My screen is visible. Good evening, everyone. I am Haripriya, PhD student from IIT Tirupati. Welcome to week 2, course name System Design through Verilog. So week 2 we will cover half adder, full adder, ripple carry adder and comparative circuits. The first circuit, let's start with the half adder. So like now we can see like first is 0 plus 0 will be the carry and sum part will be sum 0 carry 0. So in the same way we will obtain like 1 plus 1 is carry will be 1 and then sum will be 0. So from this we can obtain the equation this 2. So we will get like sum is equal to x exclusive order with y and then carry term will be a and x and y. So the logic diagram will be like the exclusive OR gate and then AND gate. So x, y, and this will be the sum part and this will be the carry part. So to write the Verilog code, do we need any wires here?
No, ma'am.
Yes, so we will be defining this x and y as input and the sum and carry will be the output. So we will define uh, sum and carry as in output port and x and y as input port. Then this is like the gate level modeling where we are calling the primitive gate XOR gate, and this is the name of the model sum output comma input. So this is the Verilog code for the half adder. Now we will instantiate this module to create the full adder. So for the full adder, this will be the truth table. So can anyone see like how many half adders are required to implement the full adder?
2.
Yes. So I need one half adder and another half adder. So full adder will be performing 3-bit addition. So 2-bit I will apply here x and y. Third bit I will apply to this full adder half adder, and this sum I will apply here, and this carry I will forward it here. So this will be producing one sum and one carry. Now which type of gate is required?
OR gate.
So we will and carry part. So how many wires are required to define this full adder circuit by instantiating the two half adders?
3 wires.
So here I will be defining one wire say S1, and then here I need one wire C1, and here I need one more wire C2. So we need S1, C1, C2. So first half adder output is S1 and C1, input is X and Y. The second half adder output is C1 and then C2. the inputs are S1 and Z, and the OR gate where the output is C and the two inputs are C2 and C1. And then to define now 4-bit triple carry header, how many, we will instantiate the full adders now. So how many full adders are required?
4 full adders.
So we will be propagating the carry, and then so this here we will add V naught, A naught, and A1, B1, B2, A2, B3, A3. So this will be the input carry C in, and then we will be propagating this C out to the next stages. So, and this final carry we will obtain as C out, and then some S0, S1, S2, and S3, and then like now I need to define this as a wire, so I will name it as like C1, C2, and C3. So for this, how many wires are required?
3 wires.
Yes. So the Verilog code will be first we will define the output port, which is like 4 bits, uh, S0 to 3, and then C out, which is 1 bit output, and inputs are again 4 bit A, 4 bit B, and 1 bit C in, and 3 wires C1, C2, and C3. Yes, please. Someone has raised the hand.
Yes, ma'am. I have a question. May I? Ma'am, why we are using vector in cout module port declaration? Why you use vector?
To define as 1 bit register. I like here I have started with S. So the next it will consider this also as 4 bit, but I want this to be 1 bit. So I'm defining as 0 down to 0.
Okay, ma'am. Okay, got it. Thank you.
Once and like start output C out from 3 down to X. You can write. This may be one type of uh, writing of this statement. And then I am instantiating the full adder 4 times. The first full adder, the output is S0 and C1. This is wire which I will be propagating to the next full adder. And inputs are A0, B0 and Cn. And this C1 is propagated to the second full adder output, input, and A1, B1, and output is C2, which is propagated to the third full ladder input, and C3 is propagated to the fourth full ladder, and the output of fourth full ladder we get C S of 3 and the final carry output. So this is the implementation of 4-bit triple carry adder, where we are like triple carry because we are propagating the carry. And then next is one's complement or two's complement binary subtraction. Okay, so if we consider like first let us take one's complement subtraction. Till here everything is clear, right? Any doubts?
No, ma'am.
So take some example. 1 0 0 1 minus 111. So for this alone, I have to take 1's complement because this is a negative number. So I will be getting like 0 1 1 1, and this number will come as it is 1 0 0 1. Now I have to perform the addition. So it will be 1 1, sorry, 1 plus 1 will be 0. I'll get 1 carry. Again 1 plus 1. Again 1 plus 1 will give 0. 1 more carry. 1 plus 1 0. 1. 1 plus 1 0 and 1 carry. This is the end around carry. We have to add this end around carry. So we will get 000 1 as the output. And when we have this end around carry, the number is positive number. And one more example. Let us take the number to be like when we how we obtain the results to be negative. So 1000 minus 8 minus 10019. So it is this I have to take 1's complement. It will be 0110, and this number will be as it is because it is positive, and the result will be 0111. There is no end around carry. So the number is negative, and we have to take the 1's complement of the result, which will be 001. So the 1's complement has this disadvantage that we have to add this end around carry. So popularly, like mostly computing systems use 2's complement method of subtraction. So in the 2's complement method, for the negative numbers, we have to take the 2's complement. So if it is 0001, 100, 000, and this number we have to subtract. So we have to take the 2's complement of it, which will be like, it will be 0 111 plus 1, 0 1 0 1 0 1. So we are not adding the end around carry because we have already like performing the 2's complement. So 1 we are adding here itself, and this number is positive, so I'm writing as it is. And the final result, I have to add 100. 1 plus 1 is 0 1, and this end around carry I can leave it, and the result is positive. So if for the next example, if we take 1000 and then this one, so now I have to perform 2's complement for this. Yes, and the 2's complement for 1001 will be 0110 plus 1, 1110, and the result will be 4 ones. I don't have any end around carry, so the number is negative, and I have to take the 2's complement of this result. So I will get 40 plus 1, which is nothing but minus 1. This is also next to. Is this subtraction clear? 1's complement and 2's complement based subtractions.
Yes, ma'am.
My voice is clear, right, today?
Yes, ma'am.
Now we will perform the adder subtractor in the same circuit. So like we will have, say, one select line, say M. If it is 0, we will perform addition. and we will take, say, m is equal to 1, then we will perform subtraction. So addition and subtraction, the difference is the 2's complement of the negative number, and we are taking 2's complement, so we have to take the uh, not of the output, like sorry, the input, say this is negative number, and 1 plus 1, this operation we have to perform. So I can use an XOR gate to take the inversion. Say if I have m, if it is 1, then say if it is 0, I will get 1. If it is 1, I will get 0. I will perform the NOT operation and I will add this m to the adder. So to perform like 4-bit, already we have seen the 4-bit triple carry adder, so we will use the same 4-bit RCA. Is the 4-bit only one 4-bit RCA like enough to perform the 4-bit adder subtractor both parallelly? Yes, it is not sufficient because if we have a negative number, then we have to again take the 2's complement. So now let us like perform a minus b. So I have to take the apply a as it is. So a0, a1, a2, a3, and then b I have to take the 2's complement. So I will apply through the XOR gate. B, B3, B2, B1, and then B0. The other input will be tied to the M, which is our select line M. And this M I have to apply as a second input C into the this bit I have to apply here as a C in. So this will be my M. Now I have obtained the 2's complement of the second input B, which is minus B. Now if M is 0, we will get the same B0, B1, B2, B3. If M is 1, we will get the complement of B0, B1, B2, B3, and M will be the C in. It will be 1, so we will obtain the 2's complement. This output, say we will get 4 bits plus 1 C out. So let us like take this as intermediate wires Q0, Q1, Q2, Q3, and this one C out. So now if C out is 0, then the number is negative or positive?
Positive, ma'am.
When C out is 0 and C out is 1. So when I need to take the 2's complement, when C out is 0 or when C out is 1?
C out is 0, 2's complement.
Yes. Yes. I need to have when C out is 0 and I am performing subtraction. When I am performing addition, if I have a carry, that is like an overflow carry. But when I am performing subtraction, then only that overflow will indicate that I am having a result which is negative and I need to take the 2's complement again. So I will apply through another AND gate. Let this be D and this be Q. So now we have to take the 2's complement again. So we need another 4-bit RCA. So this inputs I will be performing the complement if Q is 1, when C out is 0, and I am performing subtraction, that is M is 1. Other input will be this Q, and this Q I will again apply as the C in, so that I will obtain the complement 1's complement plus 1 2's complement. And the other 4 inputs, what can I do with this other 4 inputs? So because RCA will have 4-bit RCA, so 4 bits for B and 4 bits for A. So like for this G3, G2, G1 and G0, what can I apply?
Ground.
Yes. So I will add this 0, and then the final result S3, S2, S1 and S0, and this will give me C out 1. So this is the 4-bit adder subtractor module. So we need 8 XOR gates to perform the complement of B input and the output of the first RCA. So Q and one AND gate and one NOT gate. And the intermediate wires will be, the wires will be this one G3 to G0, R3 to R0, Q3 to Q0, and this T, Q will be the intermediate wires. So is this 4-bit adder subtractor module clear, or any other
Yeah.
question? Yes,
Ma'am?
Once explain the circuit again, ma'am. I'm little bit confused.
yes.
Ma'am, I have another doubt.
I will drop the circuit. So for the 4-bit RCA, we need, uh, adder subtractor, we need two 4-bit ripple carry adders. One to perform the first step addition or subtraction, and then the next RCA to take the 2's complement of the result if the result is negative. So like first RCA, let's start RCA1. So this is 4 bit. So we will have 4-bit input B3, B2, B1, and then 4-bit A input A0, A1, A2, A3. Okay, and then here also we have to define some wires. So B0, and then B1, B2, V3, and this we are applying to M.
Ma'am,
Yes,
why are you using XOR gates?
yes.
Any reason?
Like if you say now here you will get uh, 1, 1, 0, 0. So if one of the bit is 1, we are if one of the bit is 1, the other bit its complement we are obtaining. 1 means we are obtaining 0. If it is 0, the other bit is same as it is. Okay. So when it is 0, it is acting like a buffer. When it is 1, it is acting like an inverter. And I want B is like minus B, A minus B. So I have to take the 2's complement of this B. So I have to first apply this B through a NOT gate, and then I need to add 1 to this to get the 2's complement result. Is this clear? Like
Yes, madam.
we will have like B bar plus 1. So for that I need an inverter. It should act like an inverter when M is 1. That time it will be a subtractor module, and if it is 0, that time it will be an adder module. And I have to, this will give me the negation output. Now I need to add one more 1. So I will add here this Cn to be again M. This will be giving me 4-bit output and 1 carry out. See out, and like this, let me name it as Q3, Q2, Q1, Q0. This much is fine.
Yes, madam.
Now when I have say my C out is equal to 0, I have to take the output 2's complement, because the result will be negative. This we have seen before itself. Like in the 2's complement subtraction, you can see whenever the carry is 0, the number is negative and I have to perform 2's complement. So, and when the carry is 1, the result is positive. So I need not perform the 2's complement. And this we have to perform only when I am doing subtraction. So I need M to be 1. If M is 0, then the addition, the carry will be the overflow carry. So that time I need not take the 2's complement. So now I have to apply this condition. So when carry is 0, so that I will get C out bar, which is like, let me name it as a T, and I need this M bit to be 1. That time I have to perform the 2's complement of these bits. So again I will apply this through an XOR gate to perform the complement of this Q output, and then the other input of this Q will be this output, which is nothing but M and T, or M and C out bar. So I obtained the 4 inputs R0, R1, R2, R3. I am performing the 2's complement. So the other 4 inputs, so let it be like G3, G2, G1, G0. I will ground it. So it means I will apply a 0 logic. And now this I will apply to another 4-bit RCA, ripple carry adder circuit, or any other adder 4-bit adder circuit. And this carry again I have to apply this Q bit. So now this output will be our final 4-bit adder subtractor output. S3, S2, S1, S0, and this will be our final C out. Is this clear now? Is it fine?
Yes, madam.
Yeah.
Fine. Thanks.
Hello, ma'am.
Yes, please.
Yeah, hello, ma'am.
Yes, please.
Ma'am, could you please explain if you're using this circuit for addition and the A and B inputs are all ones? I mean, four ones, four ones.
Okay, I will change maybe the pointer color once.
Yeah. It's violating. I mean, as the relation, we need to get for ones and zero. Yeah, explain it me. Explain it. I
No,
just want to
no,
please.
no, please share. I'm not able to understand it. You want me to keep the input as 4141s.
Yeah. Yeah, and the operation is addition.
Okay, addition.
So the n will be zero. Yeah.
Okay, so this is 4 ones, and m is
Yeah.
0. So this will be,
Zero.
again, this will perform the 4-bit addition, like 1 1 1 1 1 1 1 1. So
Yeah.
0 1
One.
1, someone
One.
carry 1.
Yeah. One.
Okay, so now I have a
Yeah.
carry 1,
Yeah.
and then this will be 0, and
Yeah.
this will be 1.
The n output will be
No,
zero.
sorry, m is 0. So q will be 0.
Yeah.
And
Yeah.
here I am having 3 1 and 0. So
Yeah.
this is already 0, so this will act like a buffer, so I will get 0 1 1,
Yeah. Zero.
and here all
Yeah. All zeros.
this will be again 0, so the final output will be 1 1 1 0. And this is,
What will be the carry? Huh? When the carry you are getting.
yeah, this is 4-bit addition, so the result is only 4-bit. The last bit is like truncated, removed, and this will be,
So then, so we don't use carry out for both addition and subtraction. We have to neglect.
no, it will be, yes, this will be giving me the 4-bit results only.
Then for other, then it will be okay.
Wait,
Okay.
wait, wait. This is C out.
Could you give-
This is
Yeah.
C out one. This is intermediate results. This is just a wire. This is the
So if you take it as, then you will getting the wrong answer. Then the result will be wrong
it will be
because
1 1 1 and 0.
yeah, you are getting 1110.
No,
So how come?
this is the final C out result,
Yeah.
and this is like C out one. This one intermediate result.
So the one we are taking
This
from the first four-bit RCA will be the C out.
yes, yes, yes.
Okay, okay. Yeah, that's fine.
Maybe other combination you
If
can
check with
try.
another.
Uh,
Yeah, if you check with another combination, then this will be this circuit will be violating.
okay, maybe
Yeah, I will check.
other
Yeah,
combination you can try, and next week maybe we can discuss if it is violating. But this should be the
yeah,
final.
sure. For the subtraction, it will be fine. Like all combinations are perfect. For the addition of four ones and two ones will be not satisfying.
This only we will be declaring as C out. For addition, this circuit, the bottom circuit we won't use. So
Okay.
this will be like completely addition of 0. So only this will be the final result, and this will be the carry.
But how can we define it in the code, man? Like
No, this
for
will
the
be defined
subtraction
as
one.
C out, and this will be defined as C out 1. So I think this will be defined as wire only.
Okay.
Our output
Oh, yeah. Not actually not.
C out S3, S2, S1, S0 will be the output. Once try with other combinations. If it is like not coming, we can Maybe next Tuesday we will discuss.
Yeah, sure, ma'am. Thank you, ma'am.
Any other doubts? Code, maybe like we can try executing it using the EDF playground. So next I'm going to the 2 cross 2 multiplier circuit. So for multiplier we need which and all blocks like this. So say like I wish to perform A1, A0, B0, B1 2-bit multiplication. So I will get A0, B0, A1, B0 and A0, B1, A1, B1. So now I have to perform the addition. So I will get A0, B0 and with the carry I have to perform the addition. So I will get A1, B0 plus A0, B1 plus B carry 1. And this will give me some result I will keep here, and the carry I will propagate to the next stage. So I will get A1 B1 plus this C to carry. Is this like clear? Fine. Okay. So first like let me take this line A0 and then so I need AND gate, so I will perform A0 and B0. I will directly get the 0 this result. The next carry will be like this is direct AND gate, so I need not have any added block. The next will be I have to perform B1 and A0. This one I have to add with A1 and B0. So I need another AND gate. I will apply this first. A1, A1, B0 and B0. So I need A1, B0. So I need this result. So half adder will be like sufficient. And then C1. For this we will have one more carry and this one A1, B0. Sorry, A1, B1 and A1, B0. This we will be applying through another half adder and we will be getting C2 and then C3. So this is the 2-bit 2 cross 2 multiplier. Is the multiplier circuit clear?
Yes,
Madam,
madam.
can you explain the circuit one more time, madam?
Yes. So here I am having two inputs A0, A1. So first I need to perform A0, B0 AND operation. A0, B0 AND operation. A1 and then A0, B1 AND operation. Followed by A1, B0 and A1, B1 to AND operation. Next I have to perform the adder. So this will be 0. So I can directly take this. A0, B0 I can directly take as C0. and then A0 B1 I have to perform AND operation with A1 B0. So I will obtain A1 B0 from this gate, and this will be giving me the sum output and then one carry. This carry I will have to add with A1 B1, and the circuit is A1 and then B1. That I will add, and then that sum will be C2, and then we will obtain the carry C3. So this is the multiplication of A0 B0 with A1 B1. Is this clear? It is clear now, or should I explain it again? Can I read?
Okay, ma'am. Okay, ma'am.
Same way, next we will proceed for higher multiplier, higher bits multiplier, 3 cross 4 cross 3 multiplier. So for 4 cross 3 we need, say, like, I will take this as A, I will take this as B. So A will be 4 bit and B will be 3 bit. So the same way I will like directly multiply B3, B2, B1. Okay, let me take it in this side. B to be 4 bit and then A to be 3 bit. So I have A2, A1 and A0. Then I will obtain A0, B0, A0, B1, A0, B2, A0, B3, and then here again A1, B0, A1, B1, A1, B2, A1, B3. And then here I have A to B3, A to B2, A to B1, A to B0, and this I will obtain directly. These 2 bits I have to perform addition. So now I can like take a 4 bit RCA and perform, right? I have a 4 bit, so here I can like take a 0. This 4 bits I can perform, apply to an RCA ripple carry adder, and again here I will have one more ripple carry adder. Is this fine? Clear? Let's try to draw the circuit. A0, we will have an AND gate, and then we have to generate all the AND terms with A0. So A0, B1, A0, B2, A0, B3, and then again another 4 bit AND terms with A1. A1, A1, B3, A1, B2, and A1, B1, and A1, B0. So this 4 and this 4 only we have to apply through the one RCA network. So this we will get directly. We can take this as the C0, and this 4 bit RC. So now I have to define some intermediate wires. So W1, I will start with this one. W2, W3. I need one more input. So I should append with 0 and then W4, W5, 6 and then 7. This will give me one carry output, final sum multiplier output C1, and this will be giving me 4 other outputs. So define P3, P2, P1, P0. So this I will apply through another RCA, another 4-bit ripple carry adder block. So now I have to add with A2. So A2 V3, A2 V2, A2 V1, A2 V0. So the final output will be C6 final carry out, and then there will be 4 sum outputs C2, C3, C4, C5. So if I am performing multiplication of 4 bit into 3 bit, the final output will be how many bits? Say the maximum is into. Is this fine? Like the final output will be 7 bit. So this is this the 4 cross 3 multiplier clear? Hello?
Yes, ma'am.
So this intermediate wires W1 to W7 and P0 to P3, and okay, this one here again I have to define W8, 9, 10, 11 as the intermediate wires. So shall we proceed to the code? So live NPTEL is going on, sir. Sir, sir. So till this, is it fine? Shall we proceed to
Hello,
the code?
madam.
Yes, yes.
What about P0, P1, P2, P3? Those are not whites.
No, they are also wires.
Then why don't you mention, madam?
I have
You
mentioned
have mentioned only 8, 9, 10, 11 whites only.
no. I'm mentioning with W for the output from this AND gate. Then the product terms from this RC I'm mentioning like P. It's just for variables. So all this one W will be wires,
Okay.
and then the AND gate terms, the product terms, like I am mentioning W variable, its variable name, and while defining, I will declare this also as wires. And this is final output. This are final output. This is final output, and this one A1, this will be A2. So A0, A1, A2 will be input, and B0, B1 will be input. So we will have W1 to W11 and P0 to P3 as wires.
Okay, madam.
So code we will code is the code visible?
Yes, ma'am.
We will try this.
It's not clear, madam.
We will try this in the EDA playground by running this code. So I have defined this W and P as the wire, and I am, instead of saying like P1, P2, P3, I am defining it as a register. So while calling, I will call P of 0, P of 1, P of 2, like that. And here itself I am defining the 7 outputs, 3 bit A and 4 bit B, and I'm like generating all the 11 W by applying through the AND get primitive cell, and then instantiating the ripple carry adder 2 times. Okay, this we will try it. Okay. Then next, comparator circuit. Uh, 1 bit comparator.
Madam, please go back to the program, madam. Binary multiplier program.
Okay.
Please once again explain that.
We will like write the code ourselves, like from first itself. I will write in the EDA playground and try execute it and show all the codes. I thought like first I will cover for some half an hour or 45 minutes all the theory concept. Briefly I will
Okay, madam. Okay, madam.
then some assignment, and then like let us like try executing this. So for the comparator also, okay. So this is 1 bit. So A0, B0, 2 bits. And then we'll have equal, greater than, or less than. So for equal, we will define like E0 equal, and then G0 for greater than, L0 for less than. So 0, 0, 1, 1, 0, 1, 0, 1. If it is 0, 0, then it is equal. Now A is greater. Here B is greater, like A is lesser. If I am trying to implement like A greater than B, A less than B, and A equal to B, and this one will be 1. So I will get 1 when both are 0 or both are 1. So E not equation will be A not NOR gate of B not, exclusive NOR gate, X NOR. So and then G naught will be when A0, B0 bar, and L0 will be A0 bar, B0. Is this like fine? The equations. So now next the code will be direct implementation of this equation. So X naught E0 will be A0, B0, and NOT gate to obtain B0 complement and another A0 complement, and then AND gate of this is implementing A0, B0 bar, and here we are implementing A0 bar, B0. And then so this is the equation for greater than, this is the equation for less than. and here I have implemented the equation for equal to, and then we need intermediate wires like to store this value and this value, so I'm defining two wires and three outputs E0, G0, L0, and two inputs A0 and B0. Is this one bit comparator clear? Fine. Any doubts in this one bit comparator?
Madam, is there any order required to be followed here?
No, order it is our wish. Like it will all are under continuous assignments, so everything will be executed. At time 0, all the gates will receive the input and everything will be executed.
Okay, madam. Thank you.
And then for 2-bit comparator, we will be having 2 bits of input. So A will be A1, A0, and B will be B1, B0. So for equal to, like if I have to check the equality, then I need both A0 to be uh, equal to B0, and A1 also should be equal to B1. That means if, so here we can say like E2. So if I take E2, I need E1 and E2. So this I will apply through like E0, E1 I can get through the 1-bit comparator output, and then again I have to perform AND gate operation to get the E2 equality. So equality we can get directly. So I need, let me take two 1-bit comparators. So I can compare A, A1, B1, and then B0, A0. And then this output I will get E0 and then G0, L0, three outputs. Again here E0, first bit, so E1, G1, L1, three bits. Now I have to perform the AND operation between E1 and E0 to get E2. Okay. Then second, if we want to check for G2. So if my A1 is greater than B1, then the final result will be greater. So whatever the like A0 or B0 is, or if A1 is equal to B1 and my A0 is greater than B1. So I need G0. If this is greater, or I need two conditions. Either the previous the A1 this bit it is equal, or this statement I need to execute. So AND operation with A0 greater than B0. So this is greater than symbol. I need to perform AND operation with this. So this will be giving me G2. Then L2 we can directly, like if as we have implemented this 2, we can say L2 if E2 is also 0 and also G2 is 0. or again, like if we are implementing through equation L2, if the A1 is less than B1, and otherwise if both the bits are equal and the LSB bits are less. So again, like I need one more OR gate. So this input, if this is lesser, then it is fine. Otherwise, this both should be equal. MSB should be equal, and the other previous bit should be lesser. So this will be my L2. Now I need two 1-bit comparators, and the input to the 1-bit comparator is A of 0, B of 0, A of 1, B of 1, and the output is E0, G0, L0. Same way E1, G1, L1. Next, I need to obtain this AND gate where I am applying E2. This is gate 1. I am applying E1, E0 and obtaining the output E2. And then I am applying getting the second G2 gate, where this I am storing with some wire W1, and if this bit is greater or and this bit is equal, or the MSB itself is greater. So this is W1 or G1. Then next, for lesser than, we will have this as G3 gate. So either L1 should be 1, or it should be L0 should be pressed here, and this should be E1. Okay, so L, E0, E1, L0, and then the output I'm storing it in W2. So W2 or L1, I will get L2. So I need W1, W2, two wires here, and then this intermediate results, which has the output of the 1-bit comparators E0, E1, G0, G1, L0, L1, I will define as wires. The final output will be the comparison of the 2 bits, so E2, G2, L2, and 2-bit inputs. So I want B also to be 2 bits, so I am not defining any, like again redefining this. So if it is once I define like 1 down to 0, both will be 1 of 2-bit registers. So this is the code for 2-bit comparator. Is the 2-bit comparator clear?
Madam, what is a primitive?
Primitive, like there are two types of primitive. It's like you cannot break it down further. It's a predefined gate. So in the Verilog, we'll have some primitive gates. Say for AND, it will be defined as when it is 0, 0, the output should be 0. So this complete truth table will be defined in the Verilog library, it's Verilog itself. So if you instantiate this AND directly, you will get this truth table. So the other method is user defined primitives, where as a user we can define. So like if I want to define this also to be having the truth table same as AND gate, I can define it. So that time we will be using user defined primitives.
Madam, in this program you have used two wires, no, madam?
Two wires, and other for 1-bit comparisons which I am obtaining from the 1-bit comparator, that also I am defining as the wire only.
Okay, in 1-bit comparator you have used two wires.
Yes, in 1-bit comparator I have used two wires.
Two wires, now total four.
Now I need 3 outputs plus 3 outputs, 6 plus 2 8 wires.
8 wires. Okay, madam.
So as like I'm directly assigning the values through the gate. This is the gate level modeling. So I'm performing everything as continuous assignment. So I have to define everything as the wires only. If I'm using any always block, then I will be defining them as registers. So any intermediate wire I have to either drive as a wire or as a any intermediate net I have to drive as a wire or as a register. If I am initializing inside an always block, then I will be defining as register. If I am like continuous assignments I am performing, then I will define as wire. Is it? Is this clear? Fine. Now clear? Any doubts? Now that like 2-bit comparator is fine, right? Any doubts? So let's proceed then with some of the previous year assignment questions. So which of the following statement is true with respect to the structural code? A full adder implementation using 2 half adders and 2 input OR gate. So how many wires are required to implement a full adder using 2 half adders?
3, madam.
Yes. So we have already seen the full adder using half adder. So here we need 3 wires. First full adder carry and some as 1 wire, and second half adder carry as 1 more wire. Total 3 wires. So the answer is D. Next is the minimum number of wires required in the implementation of 4-bit RCA using 4 full adder circuits. So for the RCA circuit, how many?
2, madam.
How many? Sorry.
2.
Any other answers? So for propagating the carry, I need the wire. I have to define as the wire. So I will be having 4 full adders. So for this, do I need any other gates? 4-bit full adder other than full adder circuits?
No, ma'am.
So here I will need one wire. Here I will need one more wire. Here I will need to have, I have to store this as another wire. This will be the
Okay, madam. 3, madam. 3.
yes. So we need 3 wires in the 4-bit ripple carry adder. Now the 2's complement of 1110 I have to store in a 4-bit register only. So like, can you start like someone say what will be how we can start? First step, 2's complement of 1110.
We have to do one's complement of the number, madam.
Okay, so 0001.
And we have to add 1 to the first.
Yes, so it will be 0100. So B option. And then the optimal structural Verilog code for 4-bit 2's complement binary adder subtractor can be used or obtained by instantiating. So in the adder subtractor module, how many times did we instantiate the 4-bit ripple carry adder?
Twice.
Twice.
Yes, 8. 8 o'clock. So we have to instantiate 4-bit triple carry adder twice. So one time for performing the A plus B or A minus B. The other time for the second time we are instantiating for taking the 2's complement. The minimum number of wires required in the 1-bit comparator circuit. So
2.
2 for both the negation, not operations. Like for performing A0 bar B0 or another wire is required when we perform A0 B0 bar. So to store this results, we have used that wires. So is this much clear? Like now we can proceed with the codes in the EDA program.
Yes, madam.
So we start with the half adder circuit. So this is the code. I will take the code directly. So here when it is written like design, there we have to write our design, and where it is written like test bench, there we will be applying the input stimulus and printing the output values. So I am taking the test bench also. So I hope like half adder module is clear, so I am taking it directly. Shall we write from half adder itself ourselves? Is this fine, right? Yes, yes. So for test bench, I have that code here. Yes. Now, is this test bench visible? Is the font size clear or not visible?
Yes, madam. Yes.
Okay. So I am defining the module and it will end with end module. So I am giving the module name as test bench. Whatever the values are as the input in the module will be defined as registers, because I have to store and apply those values. So I am defining x and y as input, and sum and carry, which are the output, I am defining as wire. I'm instantiating the half adder module, and this is the name, the design under test user defined name, and I'm writing like output followed by input, and I want to initialize these values once. So I'm defining in the initial block, and this is begin and end. I am defining all the 4 combinations, and inside the always block I'm directly like just printing the value of S, C, X, Y, and in the decimal format. Or you can define, if you want binary, as the percentage B, or say percentage O, or like percentage H. So this is the test bench for the half-adder circuit. Is this test bench clear?
Yes, madam.
So I have to select the tool. I am choosing the first option, and the language is Verilog. So yes, we have got all the 4 combinations of the half adder. 0 plus 0 is 0, 0 plus 0, 0 plus 1 is sum 1 carry 0, and again 1 0 sum 1 carry 0, and sum 0 carry 1. So now to implement the half adder full adder module, we have to instantiate this half adder 2 times. So here itself we can, like, the double slash is used for the command, single line command, and this one slash, and this is used for the multi-line command. So I have implemented the half adder module. Now here I will take the full adder module. So this is my full adder. So my full adder is having 3 inputs, 2 outputs, and then 3 wires for storing the first full adder's sum and carry, and this carry of the second full adder. And we need to instantiate 2 full adders and 1 OR gate. So sorry, 2 half adders and 1 OR gate, and half adder will be this module. So it will instantiate. Now to modify this test bench, for me now the inputs will be x, y, and z, and output will be sum and carry only. And to the half adder, now I have to instantiate full adder module and not the half adder module. So, and then here I have to apply s sum carry x, y, and then z. So if I'm like changing the order, so I can either pass the values by using this statement dot s and pass the value. This is one of the method. Okay. So, and then here I have to define again the combination set value for z. Z is equal to say 0. So I can like define all the 8 combinations. And then I have in the dollar monitor we will be having one more input value, %d. So y and z sum and carry. Okay. So yes, we have obtained the sum and carry values for all the 8 combinations. So if my input is 1 1 1, then the final output will be 1 plus 1 plus 1 3, which is 1 1. Is the full adder Verilog code and the test bench clear? Fine.
Ma'am,
Yes.
can you explain full adder with using the logic gates like the half adder, madam?
Like
Using XOR gate, AND gate, and XOR gate, AND gate.
without using half adder, you are asking.
Yes, madam.
Then we may have to use the I need this truth table. I'll copy this. So now I have to like implement the equations. So my sum will be this one, this one, this one, and here. So if we write also, we will be getting we cannot minimize using K-map because it will be coming with some XOR operation. So now for this we have to like directly write the equation. So like I will write the equation sum has x bar y bar z 0 0 1. Then after that I have x bar y z bar, and then x y bar z bar plus last one is x y z. This will be my sum equation. Now I can take x common from here, so I will get x bar y bar z plus y z bar. This is in the form of some exclusive OR, and again x y bar z bar plus y z. This is in the form of XNOR gate. So I will get x common, x bar common. Here exclusive OR y, exclusive OR with z, and with x I will have exclusive NOR gate. Okay, so this is in the form of x bar y plus x y bar. So I will have x or y and z. So this is my sum equation. Same way for carry. Okay, this we can minimize. So I can write it in the form of a K map. So K map will be, I'm taking the z here, xy. So this will be 0, 1, 2, 3, gray code, 4, 5, 6, 7. So 0, 0, 0, 1, 1, 0, 1, 1, and then 0, 1. So I have to be like this is 0, 0, 0, and then 1, and then 0, 1, 1, 1. So this will be 3 combinations of 2. So C I will get A, B, the value which is not changing, sorry, okay, x and y, x and y, and then this will be y and z plus z and x. So now I can implement this directly. So I need, say, 1 3 input XOR gate, sum bit x y z, and then xy yz and zx. And then perform the OR operation to get the final sum. So this will be the full ladder with directly using the gates. Is it fine?
Yes, madam, but how can we write the code, madam, Verilog code using these gates?
Yes, so now I need to define one wire here, W1. Here one more wire I need. Here I need one more wire. So first I will call the XOR module and some gate name, and then output will be, say, S X Y. Okay, 3 gate. I'm not remembering the code word. Okay, so if we are using 2 exclusive OR gates, then 2. So we can use 2-bit exclusive. So here again I need to define one more wire. So I will apply W4 XY. Again I will pass through one more exclusive OR gate, and then now final S W4 is Z, and then AND gate G3 W1 XY. Then again AND gate W2 Y Z, and W3 will be ZX. I will apply through AND gate, and then final result I will apply through one OR gate, which will be like, okay, I will take W5, W1 or W2, and then W3 or this one W5. I will store it in final C. So here I am getting the C value, and here I am getting the S value. This also I am trying to implement like this. W1, W2, W3. Here I need one more wire, so W5. So the input will be X, Y, Z and output will be S and C. Is it clear now?
Yeah, madam. Fine, madam.
So after the full adder, our next module is full adder 4-bit triple carry adder. So now I have to instantiate 4 times this full adder module. So I'll apply here 4-bit RCA. Now I have to change this test bench accordingly. So now here my inputs are 3-bit, 3 down to 0, A and B, and one more Cn is also input. My outputs are S, which is again 4-bit, and my C out is 1-bit. So I have to instantiate bit 4 and RCA, and I have to pass the values C out. So same order I'm passing. So I'm directly writing the values S, C out, and then it is A, B, and then C. And my A is 4-bit value. For tick B, I will take 001, and B is again 4 tick B is 1, 2, 3, 001. So here also I have to change my display as C out, A, B, and then C in. This will be S, C out, A, B, C out, and yes. So okay, we are getting, don't care. So any error in the test bench or code? This is AP, this is wire. Again, I have wire which is S, and C out is also wire 1-bit. And for the 4-bit RCA, I am applying S, C out, A, B, and then C in. And my inputs are 4 tick B, 0001. So 4-bit inputs only I am applying. And I am displaying C out, A, B. Okay, C in. Okay, I have to define C in also. So now 1 plus 1 is 2. As I have displayed in decimal, you can see the decimal value. Is the code for our 4-bit RC clear? Fine.
Fine, madam.
Yes, today's class recording we will share. We will upload in the YouTube, and we will share you the link. The next code is adder subtractor module. So okay, this code copying it here. We will see adder subtractor. So for adder subtractor, we have to instantiate 4-bit ripple carry adder 2 times, and then perform the XOR operation of the B input, and then the Q, the output of the first ripple carry adder, and then this is for whether we have to take the 2's complement or not, and we have to assign the second ripple carry adder inputs to 0, and then this is the instantiation. So is this code clear or
Fine, madam.
it's fine? Okay. Now we will take the test bench. So test bench, I have A and B as input. I have directly defined A and B as input, and M is my input, selecting between adder and subtractor, and C out is my wire, and S 4-bit is also wire. So these both are outputs and these are inputs. And I'm calling this module 4-bit AS adder subtractor and passing the S, C out, M, A, comma B values. So the values are triple, for example, I'm passing it 0001 and 0001. So let it be like subtraction. Then the result should be like 0, 1 minus 1. Yes, 1 minus 1 if I perform, it will be 0. So the other question was like, okay, I think I have done some modification here. First RCA will be C out and second RCA will be C out. And C. So now if I apply 1, 2, 3, 4 ones and then 4 ones, and if this is 0, the result will be 15 plus 15. It is carry is 1 and then this is 14. It will be like 16 plus 14. So 30.
Ma'am,
Yes, yes.
in test bench, for A and B, we applied the same input, right?
Yes, yes.
We can take two different inputs, or we have to take the same input for A and B.
No, no, we can take. This question was asked before, like if it is 4 ones and 4 ones, and if M is 0, the output. So I thought like I will simulate that value. Now it is like 12 plus 15, which is 27. So 16 plus 11, 27. The C out will be in the 16th bit place, right? This will be having 8421 bits. Is this results fine or clear? Like, any doubts in this results? Like when there is an overflow, the C out bit I'm obtaining, which is the output of the first RCA. Second RCA I'm using for the 2's complement only. So it is having the C out as intermediate value.
Okay, madam.
Any other combinations you wish to try?
Ma'am, we can apply decimal or anything.
Yes.
Decimal.
So if you want to apply decimal, I will change this to D for decimal and 15. This is D. I'm keeping the values like same to show you. So 15 and 12. Here also, if we want to print in binary, we can print by using percentage %b instead of percentage %d. So we will get 111011.
Okay, madam.
Yes. Next code is for us multiplier code. Okay. This we will discuss. Now, 4x3 multiplier code. So for the multipliers, first we needed A0, B0, which we can take directly. So I'm taking it in C0, and the rest till 11 wires we were storing the AND operation, the product terms. A0, B1, A0, B2, A0, B3, A1, B0, A1, B1, A1, B2, A1, B3, and then same way for A2, B0, A2, B1, A2, B2, and A2, B3. And then these two operations, which we defined as, here we need 0. So this I am defining as x is equal to 0, and then this carry in I am having as c in as 0. So I am defining two values, c in as 0 and x is equal to 0. So here I am defining 0, and I have to apply w1 till w3. W0 to W3, then carry is 0. Output I will get as this will be my output. So, and one more 4 set of input will be W4 to 7. Okay, so I will show you here. For this, I have to apply W1, W2, W3 and 0. So I will perform a concatenation operation. Like inside the bracket, I will write this value W1 down to 3 and 0, comma 0. And I will apply W4 down to 7. And the output I will obtain is P0 to 3. And the Cn will be 0. So this is, I have defining it as P3. This I am taking as C1. So I can write my first is as C1 and the next P down to P2 and then P3 will be my carry. So P3 is my carry, P2 to 0 and then C1. This I am performing concatenation operation. So whenever you define something inside this bracket, this flower braces, so it will be like 0, and then I am combining this 0 with W3 down to 1. Okay, so in the same way, in the output also I am combining P2 to 0 and then C of 1. And then I am applying to the second ripple calendar. Here I am applying P0 to P3. And then this wire output of the product terms W8 to W11. So W8 to W11, P0 to P3 and my Cin, and then I am obtaining the result C6 has my carry and 2 to 5 has the sum output. Is this 4-bit 4 cross 3-bit multiplier clear? Any doubts in this code, or should we write it like along with the circuit diagram? Is this code clear? Multiplier,
Yes, madam.
then test ones I'm taking from here, and so I need a 3-bit register for A and 4-bit register for B and 7-bit output C, and I am applying to the multiplier C A comma B, and then I'm giving some 3-bit value and 4-bit value and printing the final result. Line number 3. Okay, this is very so 2 into 2 we have obtained 4. It's the multiplier code and the test bench clear fine. Next we have
Yes, madam.
circuit.
Ma'am, for the test bench, while applying our inputs, we are using a delay time, right?
Yes.
We can use different delay times, or we have to use the same delay time for the all the inputs.
No, it is our wish. Now if we have some flip-flop and then we go, then we have to like have that practically we need different delay, but here we can directly apply any delays. That setup time, hold time, those things we have to take care, means we have to have constraints, but now it is pure combination, and this is so here we can apply any delays. It won't be, this will not be any error. So you can apply any delay. If I want 11 also, I can apply.
Yeah, okay, madam.
Yes. Next, comparator circuit. So first we will start with 1-bit comparator, so that next we will instantiate this and assign a 2-bit comparator. 1-bit comparator, and then test bench. So the comparator, here we will be having XNOR gate for equality, checking equality, and then A0, B0 bar, and then A0 bar, B0 for the less than operator, and then less than output, and then greater than output. So if I give the input as A is 0, B is 1, so this will be output for L. I'm getting L has X, it should be 1. Output is E0, G0, L0. A0 in W2 and W2 B0 L0. Next is, let's check the greater than. Yes, for greater than G0 is 0. If I make this as 1, now A0, B0 are 1, so it is equal. This L0 is having some. W2. Okay. Now we have to check the lesser than. So now we are getting L0 as 1. Previously I have like used capital W2, so it was not driving this L0 to any value, so it was driving to a don't care value. So this is 1-bit comparator code. Is this code fine? So that like next we will proceed for 2-bit comparator. Any doubts in 1-bit comparator? So I'm proceeding to the 2-bit comparator code. So in the 2-bit comparator, I will be instantiating this 1-bit comparator 2 times, and then I need to perform this operations. Okay. So first, whether all the 3 are equal. The next, whether the G0, the LSB is greater and the E1 is equal. Then I will apply this to an OR gate, or whether G1 is itself greater. So I will get the G2 value. The same way for the lesser value, less than, whether the LSB is lesser and the MSB is equal. If this, or whether the MSB is itself lesser. So with this I will get the L2 value. Is this code for 2-bit comparator clear? We have instantiated the 1-bit comparator 2 times. Any doubts till now, till this code? So if no doubts, I will proceed with the test bench for this one. So now I am defining 2-bit input A and B, and then E2, G2, L2 for equal, greater than and less than values, and I am applying the 3 outputs and 2 inputs. So my 2-bit input, if I am keeping like 0, 0, 0, 0, so I should be getting equal is 2 as 1. So I have obtained E2 has 1. So in the same way, if I am making this as 1, that means B is greater than A and A is less than B. So L2 is 1. If I am making this bit as 1, then the output should be G2 equal to 1. G2 is 1. Any doubts? Any doubts in the full adder, half adder? Then we have used, like first we designed the half adder, then we have designed the full adder. Using the full adder, we have designed the 4-bit triple carry adder, and then 2-bit multiplier, and then we have defined the 4 cross 3 multiplier, and then the final 1-bit comparator and 2-bit comparator. Any doubts till this one, till 2-bit comparator? So like we have covered half adder and we have used half adder to define the full adder, and then 4-bit triple carry adder, and then adder subtractor using two RCA modules, then multiplier 4 cross 3 multiplier, and then 1-bit comparator, and then 2-bit comparator. Any doubts? So is everything clear? Like fine? Any doubts? Okay. If no doubts means like we can end today's section. Any other doubts if you have, we can discuss in the next Tuesday section. Thank you everyone. I'm ending the today's section. No doubts, right? Any doubts?
Madam, is this recording available online, madam?
Yes, it is available.
By today?
Yes, I will upload. I will upload in the YouTube and share that link in that document. And
PPT also, madam?
yes, PPT I will upload in the drive. You are able to access
Okay, madam.
last week PPT, right? You are able to access my last week PPT and video?
I have not tried, madam. I will try now.
Yes. Okay. Thank you all. Thank you so much.